Welcome to this explainer. Picture it, it's the early 1960s, and physicists are literally mapping out the fundamental building blocks of the universe. But then they hit a massive mathematical wall. Today, we're cracking open a cosmic cold case. We're going to unpack a mystery that was hiding in plain sight, right within the very fabric of reality itself. We're decoding the Cabbibo Theory. Honestly, it's a total masterclass in how just one single brilliant mathematical insight can completely rewrite our understanding of how the universe works. Let's get into it.
So let's jump right into the anomaly that completely baffled the scientific community at the time. You see, physicists had these non-strange particles, like neutrons, and they were undergoing this process called weak decay at a certain predictably fast rate. Makes perfect sense, right? But then they looked at strange particles, things like kaons, and their weak decay was significantly slower, like noticeably slower. And this was a huge problem because we're talking about the exact same fundamental force here, the weak interaction, but it was seemingly playing by two completely different sets of rules depending on which particle it was interacting with.
Which naturally leads us to the million-dollar question, why on earth was the weak decay acting so strangely? Why the massive slowdown? And look, this wasn't just some minor bookkeeping error or a glitch in a lab detector. No, this anomaly threatened to tear down our entire foundational understanding of the weak force. Because physics relies heavily, and I mean heavily, on this idea of universality. It's the principle that a fundamental force has a universal, consistent strength everywhere. If the weak force was just playing favorites, well, the whole theoretical house of cards was going to come tumbling down.
Enter our brilliant detective for this cosmic mystery, Italian physicist Nicola Cabbibo. In 1963, he proposed a completely radical yet incredibly elegant solution to save this idea of universality. He introduced a brand new concept called quark mixing. He basically stepped back and said, well, maybe the weak interaction isn't looking at the universe the same way we are. We thought it was acting on purely distinct, separate particles, but Cabbibo hypothesized, he said it was actually acting on a mixture of them.
And you can actually see this paradigm shift spelled right out in his original handwritten notes. His primary insight was that the weak interaction simply does not act on pure quark states. It acts on a mixture. It was a total game changer in perspective. To the weak force, the universe wasn't just operating in these stark, neatly labeled categories. Instead, it was operating in highly specific mathematical blends.
Think of it kind of like mixing paint. Rather than seeing distinct primary colors, Cabbibo deduced that the weak force interacts with the precise linear combination of down quarks and strange quarks. The force doesn't just reach out and grab a pure down quark or a pure strange quark. No, it essentially interacts with this beautifully precise mathematical cocktail of the two.
But you can't just mix quarks arbitrarily, right? The universe has a very specific recipe. And the absolutely crucial ingredient in this mix is a number, 13.1 degrees. This is the famous Cabbibo angle, which physicists denote as theta sub c. Derived straight from experimental values, this specific angle quantifies exactly how much these down and strange quarks mix together. It's quite literally the fundamental cosmic recipe ratio for the weak interaction.
And what's really wild is how this math translates visually. It can actually be thought of as physical geometry. Imagine a graph, what we call flavor space. The standard horizontal and vertical axes, those are our pure down and strange quarks. But the weak force, it doesn't use those axes. It operates on tilted axes. It's a literal mathematical rotation in flavor space by exactly 13.1 degrees. Those rotated states, that is what the weak force is actually interacting with.
So let's actually build this new physical reality step by step. Step 1, you start with your pure down and strange quarks. Step 2, you apply that precise 13.1 degree mathematical rotation we just talked about. And step 3, boom, you get your weak interaction eigenstate. We call this d prime. The linear combination formula maps out exactly, to the decimal, how much of those original pure particles make up this brand new mixed state that the weak force actually sees.
Okay, now here's where the math beautifully, perfectly aligns with experimental reality. Let's break down these transition amplitudes. For the non-strange particle decays, where the strangeness doesn't change, so delta S equals 0, the mathematical amplitude is proportional to the cosine of our 13.1 degree angle. And the cosine of 13.1 is roughly 0.97. That is a massive, nearly 100% full-strength boost. But for the strange particle decays, where delta S equals 1, the amplitude is proportional to the sine of the angle. And the sine of 13.1 degrees is just 0.22.
So looking at these original derivations, we can see exactly how Cabbibo's abstract linear combination formula translates into hard, undeniable experimental proof. It completely explains why those strange decays are so heavily suppressed. The math shows the rates are suppressed by a factor of tangent squared of theta c. So that big mystery of why kaons decay so much slower than neutrons, it's simply because the weak force is fundamentally experiencing them through that tiny 0.22 sine factor rather than the massive 0.97 cosine factor. Case closed.
So, why does all this actually matter to us today? Well, this deduction was revolutionary because it preserved that incredibly elegant idea that the weak force absolutely does have universal strength across different particle types. The force itself isn't magically changing its strength, it's just interacting with a rotated mixture of particles. By putting a hard, quantitative explanation to those suppressed decay rates, Cabbibo's insight literally became an absolute cornerstone of the standard model of particle physics.
And honestly, this single idea created a massive ripple effect through history. We start in the 1960s with this baffling discrepancy based entirely on observations of kaon decays. Then in 1963, Cabbibo steps in and introduces quark mixing and his famous angle. And eventually, this exact same framework evolved into the much larger, expanded 3x3 CKM metrics. Cabbibo didn't just solve one isolated anomaly. He laid the absolute bedrock foundation for all of modern flavor physics.
That initial two-quark rotation, mixing just those down and strange quarks, was the vital direct precursor to that expanded 3x3 CKM matrix. CKM stands for Cabbibo, Kobayashi, and Maskawa, by the way. His original framework was so incredibly robust, so fundamentally true to how nature operates, that it expanded perfectly to incorporate an entire third generation of quarks, the top and bottom quarks, which, get this, hadn't even been theorized back in 1963. It's just amazing.
As we take a step back and really admire the modern standard model, a model literally saved by a brilliantly simple 13.1-degree mathematical rotation, it really leaves us with something profound to chew on. Think about it. If the fundamental forces of the universe are operating on hidden mixtures and rotated angles that we can't intuitively see, what other hidden mathematical rotations and mixing angles are still out there, just waiting to be discovered in the fabric of flavor physics? What else is the universe quietly blending together right beneath our noses? Something to think about. I'll catch you in the next explainer.